Hi folks. In the last video, we talked about injectivity and disjointness, and I went through how injectivity works in Coq, where we proved injectivity ourselves and then used the injection tactic to have Coq manage injectivity of constructors for us. In this video, we're going to see how to work with disjointness of constructors. So just to remind ourselves, disjointness here means that no two different constructors are ever equal. There's no way to have S of n be equal to O under any circumstances. There's no way to have nil be equal to cons of anything under any circumstances. There's no way to have T2P of B be equal to BZ under any circumstances. That last one may give you pause. I talked about this in the last video. And the important thing to remember is that we're saying that T2P BZ is not equal to BZ. We're going to meet this notation for not equal in the next video, but I'm going to use it here just to get you habituated. Is not equal to BZ. And you might look at them like, no, these both are 0. It's like these both are interpreted as 0. But syntactically, these are different things. Right? That was actually the source of our problem, right? That like these mean to us the same thing, but to Coq, these are just symbols. Not everybody is satisfied with this formalist account of what mathematics is, where mathematics is a game that humans play with symbols. I'm not completely satisfied with it, but I think it's certainly the case that that's what's happening in Coq. And I think that's the case of what's really happening in math. We've just happened to choose good symbols that let us make inferences or predictions about how the world ought to work, and then we check those and see that our symbols are good ones for reasoning about the world in as much as we can understand it. That's my perspective. Um, you might have a different perspective where you think math is real, that numbers exist in some meaningful way. That's great. I think that these questions of the philosophy of mathematics are important ones and really, frankly, beyond the scope of our course. But for us, for now, keep in mind that these are just different symbols. They have different representations in the computer, even if they mean the same thing in the interpretations we apply. And so when we talk about equality, we're talking about equality of the actual representation, not about how we choose to interpret it. Philosophical rant over. If anybody wants to talk philosophy of mathematics, I'm always delighted to talk about these things. So let me know. I'm happy to chat. It's a fun thing to talk about. Let's see how it works. So this next theorem, I'm excited about. It may not be obvious why I'm excited about it, but we're starting to prove really, I think, very interesting things about the definitions we have. Here, we're going to show that, look, this is really right. Our EQB function is correct in this case. If we say EQB 0 n equals true for any n, then n is really 100% equal to 0. So we're starting to take a function that we wrote forever ago, and okay, we convinced ourselves that it was the right thing. And we're gonna get confidence from Coq to say like, no, this is really doing some of the right stuff. Your function for checking whether or not numbers are equal is really giving you right answers, right? If it says true, then in this case, they really are equal. In a couple of days, we'll be able to prove that this is true in all cases, that this EQB function is just 100% correct. That to me is a really exciting prospect, right? The level of confidence we can get from that. Let's see how it works. Okay. I'm just going to follow the propositions to start. You can look ahead at the proof script if you want, and you can see the new tactic that comes at the end. But let's just walk our way through it, because already this is, I think, an interesting proof just in its structure. Okay, we want to show that for all natural numbers n, if EQB 0n equals true, then n is really equal to 0. Let n be given. Let's go by cases on n. N is either equal to 0 or successor of some n prime. Let's use an equation to remember the value of n. We won't actually need. Okay, the n equals 0 case. N equals 0. We know that EQB 0, 0 equals true, and we have to prove that 0 equals 0. Okay, the conclusion, if you look at it, feels pretty chill to me. Like, okay, this is the case where indeed EQB 0, 0 equals true, and right, 0 equals 0. Perfect. Let's look at the S of n case. S of n prime case, excuse me. Okay, so I'm going to run simple here. And you look at that and you be like, you what? You huh? Maybe it's easier for me to intros H first. Let's see where we are. EQB 0 S of n prime is true. That's going to be false, right? So I did simple first because we don't know how to simplify elsewhere in our world yet. So here, let's simplify here. We get false equals true. Okay, intros H. So let's look at our world. In a world, in a world, in a world where false is equal to true, we have to show S of n prime is equal to 0. Okay, this seems like a thing that's hard to prove, right? Like intuitively, this should not be a thing that we can prove. I said it's not going to be possible. But look at our assumption. We've assumed that the Boolean false is equal to the Boolean true. By the same token, that shouldn't be true. So you might think like, oh, well, I can destruct this. It doesn't do what you want. The tactic that you want here is called discriminate. The tactic discriminate, you give it a hypothesis, something in your context, not in your goal, in your context. You name a hypothesis right here. Just plain discriminate doesn't do quite what you want. Discriminate H says, okay, H is a hypothesis in my context that is assuming that two constructors that are not equal are equal, right? H is a contradiction. H is not possible. So discriminate H says, no way, not even a little bit. And that finishes our proof. Okay, so the discriminate tactic is an instance of the logical principle we met earlier that we called then ex falso quod libet, from false whatever you like. And I forgot to tell you the English name, which is a shame because the English name is fantastic. The English name is the principle of explosion. Anybody else get chills? I get like chills whenever I talk about it. I love that. If you've assumed something false, then you get to blow up the world. Like you get like your like supervillain cosplay on, like $1 million, right? You get to do that if you want. Um, the principle of explosion says if you've assumed something false, you get to blow up the world. You get to say, I don't need to finish this proof. The universe is in an inconsistent state, and I don't need to deal with this, right? This is not my world. Doesn't that sound nice right now? If the universe is in an inconsistent state, you don't have to deal with it. All right, let's move on. So the hypothesis H, false equals true, is inconsistent. It's not. It can't be right. Once we've assumed this, we've assumed something false. And you can think of every proof as saying, hey, my context implies my goal. So false, a false thing, implies whatever you want. Ex falso quod libet. So once you've assumed this false thing, then you can prove any goal you want. That's what discriminate does. Let's prove some crazy stuff. Let's go. Okay. All right. George Orwell to the front desk. If successor of n equals 0, then 2 plus 2 equals 5. George Orwell, you have a phone call, come to the front desk. Nobody does this anymore. Now we all have cell phones. But it used to be that like you would tell people where you were. And you'd say, hey, yeah, I'm going to be at the baseball game. If I'm there, just call me and then they'll page me. They'll find me. I'll be in this set of the seats. And that would actually work. Isn't that incredible? It's a different world. Okay, so suppose it's a natural number n such that s of n equals 0. Let's prove that 2 plus 2 equals 5. Well, 2 plus 2 equals 5 if you assume that successor of n equals 0. Sure, right? Like, what? Don't even joke about this. Not even this, right? Discriminate contra. Blow it up. Okay, let's do it. Let's do another one. No numbers. I don't really like numbers. If false equals true, then the list n is equal to the list m. Okay, let n m be given such that false equals true. Sorry, that contra, that's not going to work. False does not equal true. Blow it up. If you're uncomfortable when you get to this point, I feel you, right? Like this is like an unhealthy moment. You're like, you look at this and you're like, no, false equals true. I don't want it. And I want to make it clear that it sounds like having false things in your context is bad, right? Like maybe you're responsible, maybe something bad happened. Like here you have this goal that seems really hard to prove. Like we don't know anything about N and M. Why would these lists be equal? I don't know. But having something false in your context is reason to celebrate. It means you're done. You finished the proof. If you can convince the universe in your proof, right? You can think of your proof as a game with the universe. If you can convince the universe to put something crazy in the context, something on the face of it false, then you've won. You've tricked the universe, right? You say, yeah, oh sure. If false equals true, we can prove whatever you want, right? It's like just like not a big deal, right? Like this is absolutely crazy town, and the universe is the sheriff. So like blow it up. False equals true? No way. When you see something contradictory in your context, you've won. Okay, I want to conclude this video with a couple of quizzes just to sort of see where we're at for injection. Okay. Suppose Cox's proof state looks like this. X and Y are Booleans. We know that neg b x equals neg b y. And we apply the tactic injection H. What will happen? Pause the video if you need to. Think about it. Okay, let's look for a bit and understand what the consequences of each of these mean. 1, no more sub-goals would mean that injection solved our goal. 2, the tactic fails would mean that for some reason injection doesn't apply here. 3 means that injection applies and then we get this equality out. 4 means something else is happening and we haven't outlined it. I'm going to be nice, it's not 4. It's also not 1. Injection never solves your goal. Discriminate solves your goal. Injection, no. So it's really between these two. Does the tactic succeed and you get x equals y implies y equals x, that same sort of adding stuff to your goal business? Or does the tactic fail? Think about what you believe here. What did we define about injection? What did Cox say was injective? Constructors. Is neg b a constructor? No. Neg b is a function that we defined. The answer is 2. Tactic fails. Next one. Now suppose that Cox's proof state looks like this. X and y are nats. We need to prove that y equals x. We have x plus 1 equals y plus 1. We do injection H. What will happen? I want to draw a connection here. Those of you who attended Sri Krishnamurthy's talk about transfer, this is the same problem. We have two variables, different types. Okay, sure, different types, but two variables. Here we have an equality between a function and the variables. Here we have an equality between the function and the variables. I could have changed this to plus x1 equals plus y1. Right? Those are the same. So these are just functions. These are user-defined functions. This is exactly the same situation we just saw. We've just changed the types and we've changed the functions. The answer is the tactic fails. Injection only works on constructors. Now, this is a lemma we can prove. It is the case that plus is injective in this way. Adding 1 to 2 different numbers gives you the same thing here. But it's actually going to involve some more complex techniques than just injection. Okay, what happens here? Very similar problem, but this is actually going to reduce to s of x equals s of y, if you remember the definition of plus. Like every other tactic we've seen, reflexivity and so on, apply. Coq will happily simplify before your tactic happens, which means that Coq will actually see h this way. It'll see h as s of x equals s of y. Now, s is a constructor, so injection should succeed. And number 3 will be what happens here. Okay, in the next video, we're going to start talking about inequalities. If you have any further questions about injection or discriminate, please take them to Zulib, and I'll talk to you soon. Cheers, y'all.